I'm showing a breadboarded example of a uh, regulated voltage supply where the goal is to be able to supply 3, 5, and 12 volts consistently. So there's a range of voltages that I can supply consistently on a varying load and a varying VCC supply. So essentially, it uses a Zener diode to set a reference voltage and then amplifies that reference voltage into a bigger reference and then buffers that voltage to the load. So the setup is this circuit here. And in the previous video, I created a simple Zener voltage regulator that essentially has a reference set by the Zener, and then it gets pushed to the base. So therefore, this emitter voltage drop is fixed, and the transistor here will supply as much current as the load needs to achieve that voltage drop. The drawback for this is the Zener sets the voltage reference. So in my case, I was using 3 forward bias diodes in place of the Zener, and that achieved a 1.82 voltage drop, which means after the BE junction voltage drop was it was 2.1 volts before, and then afterwards is about 1.4 volts across the load. But in this case, I want to supply 3, 5, and 12 volts. So how do I do that? Well, the first thing that I thought of was I could use I could essentially use a PNP NPN transistor setup, like in a common emitter configuration, to amplify the voltage before putting it through the current buffer. So then when I first thought about doing this, it's very simple. So there's a V fixed across here, which is the Zener diode reference voltage minus 0.7. And then if I fix this resistor, now I have a fixed current through here. And then I'll have a fixed current through the collector. And depending on what the collector resistance is, therefore I now have another fixed voltage drop across here. So by varying the ratio of this resistor and this resistor, I can achieve a fixed amplification of a fixed voltage. Uh, so basically, this voltage between VCC and um, uh, uh, the collector voltage is fixed. And that's the ultimate reference voltage that I want to get to 3, 5, and 12 volts by varying this RC. So then how do I buffer this in another stage? So a common way to buffer is using common uh, the common collector config, but it actually doesn't work here because the common collector, right? It requires the load to be connected from the um, uh, the emitter to the ground, and here uh, this is not actually a fixed voltage because the voltage is fixed between the supply rail and the base, not the base and the ground, like the way it would be in a common collector. So instead, what I used is I used a two-stage with an PMP to supply the current buffer, because in a PMP, um, the voltage drop is constant from the base to the voltage supply VCC here, because this is counted as the emitter in a PMP. So therefore, I can actually use the supply rail and the fixed voltage reference between the supply rail and the collector of the MPN to supply um, the emitter voltage in the PNP. So this is the setup. The first stage sets the reference voltage using a bunch of diodes. And then the second stage is an amplification using a simple common common emitter configuration. And I take the voltage out of the collector of the MPN, and the voltage gain is R2 divided by R3 here. And I'll show you the workings of how I set these resistors later. And then the last stage is the buffer stage, which uses a PNP to buffer, and the voltage drop across the emitter of this PNP junction is this reference voltage minus 0.7 volts across the PN junction here. Lastly, let's look at some other components, what they're for. So this resistor R4 is to drop any extra voltage that we don't need, that we don't want to burn across the PNP, because the PNP transistor has a power output limit as by the data sheet. Fortunately, I actually didn't need this R4, so I could actually just have removed it because the current was small enough for my requirements. These two capacitors here are for input signal decoupling. So if VCC fluctuates, like if it had parasitic inductances which cause the fluctuation, I wanted to bypass the load, so the load would receive a stable voltage. The other possible source of voltage fluctuation is at the PN junctions of the diodes themselves, because diodes have noise. They create noise from heat and other factors, even at a stable DC bias. That's what these two capacitors are for. Okay, so let's step through the calculations that we're setting for each of them. So first of all, we need to calculate the maximum current that's going to be going through the load, because this maximum current is going to determine how much current this base of the PNP is going to draw, and how much power is going to be lost across the PNP's collector emitter junctions. So I take the maximum possible current from a configuration, which is a 20 volt, which is a 12 volt drop on a 1K on a 1K load, which gives you 12 milliamps. And then I'm going to use the PNP, which is 2N5401. I'm going to use its data sheet to determine the gain expected at 10 milliamps, which can be 60 to 240, so it's going to be 60. And then the max power drawn is 625 milliwatts. Basically at the maximum, at the minimum power supply, it's going to be 15 volts supplied to this load, and the load will draw 12 volts. There's going to be a 0.7 voltage drop across the PNP's emitter collector to stay out of saturation. So therefore, there's going to be 2.3 volts that's never going to be needed across the PNP. So then we're going to set R4 to be able to remove 2.3 volts at the maximum current. So therefore, we can calculate R4 to be 2.3 volts divided by 12 milliamps. So that's 150 ohms. So that's 150 ohms. Yes. It's actually 191 ohms, but I have a 150 here, so I'm just going to say 150. So the reason why we didn't actually need R4 is because the power output of the PNP is the highest possible is going to be a drop of 17 volts times 12 milliamps, which is very much within the power limit. But I added this resistor just to show that if it was outside, we could still drop it a little bit. Cool. The next thing is let's calculate what this this current would be. So we're using the minimum beta for the PNP, which is 60. We know that at least IB2, the minimum possible current that we need to supply in order to make the circuit work, is 12 divided by 60, which is 0.2 milliamps. And so then now let's go to the amplifier stage. We know that this needs to at least supply 0.2 milliamps. And to create this amplified voltage supply, it's going to be a ratio between R2 and R3. But you'll notice that if we increased R2 and R3, like if we kept the ratio the same, for example, if we wanted a a 2-time voltage gain. R2 could be 4 volts, R3 could be 2 volts, and that would create a 2-time voltage gain. But we could also make R2 2K and R3 1K, and that would also have a 2-time voltage gain. So and in fact, if we made these resistance very high, it would draw less current and therefore waste less power. So why don't we just make R2 and R3 really, really high resistances? So for example, R2 could be like 10 million ohms and R3 could be 5 million ohms. The reason why we can't do that is because it needs to account for this extra current flowing through here. And what happens is if R2 and R3 are too small, are too large, the current flowing through them from the VCC would be too small, and therefore the calculation gets skewed by this extra addition of the current from the PNP. So R2 would be receiving, so in the case of like a really large resistor being used, R2 would be receiving some current through only the VCC, but then R3 would be the VCC plus this extra current. That skews the calculations on the voltage drop for R3. So what we need to do is to make sure that the calculation is not impacted, we aim for a 5% difference. So then therefore the current flowing through this amplifier circuit needs to be at least 20 times the base current of the PNP. So it needs to at least be 4 milliamps. And then now we know that it's going to be 4 milliamps flowing through here. Now we need to know the ratio between R2 and R3, and then we have two simultaneous equations to solve. So the two ratios are very simple. It's going to be the reference voltage that we have here minus 0.7 volts gives us this voltage, and then we want it to become a voltage that's minus 0.7 volts giving us the load voltage. So in this case, it'll be 2.1 minus 0.7, which means that we want 1.4 volts to be able to turn into 3.7, 5.7, and 12.7 volts. So calculating the range, so we got the simultaneous equation here, and calculating the range for R3 and R2, we got, if we fixed R3 at over here, 373 volts, the range for R2 becomes from 3000 volts to 987 volts. So therefore, in order to supply these ranges of voltages, this resistor needs to vary between 987 and 3201. And I'm not going to go through the calculation for R1, but essentially this is just, it needs to supply enough current to make sure that the forward voltage drop across the diode given by its characteristic response curve stays at 0.7 volts fixed. So let's look at the circuit. So this is the circuit. These three diodes provide a 2.1 voltage drop fix. And this secondary circuit is the amplification. There's the NPN transistor here. And then this third circuit is the PNP current buffer, providing current to the load, which is this resistor. And then connected in parallel to the load is a electrolytic capacitor, 470 microfarads, to filter out large signals, and a smaller ceramic capacitor of 100 nanofarads to filter out smaller, larger frequency noise. So the reason why there's multiple stages of filtering is because in signal filters, if we only had a large capacitor, the large capacitor, because of the way they're manufactured, they also have internal inductance because capacitors are rolled. And because of internal inductance, it leads to a resonance frequency at a higher frequency. So at that high frequency, this capacitor can no longer, this electrolytic capacitor can no longer act as a filter. So we need another much smaller capacitor to filter at that frequency. And if we calculated the RC cutoff filter's frequency and its expected internal inductance, we can calculate what that smaller capacitor is. I didn't do that calculation. I only went off, a recommendation of always having a 100 nanofarad attached to the load plus a 407 microfarad. It actually should be 22 microfarads because the rule of thumb is having 2000 microfarads per amp of current. Okay, so next let's have a look at the result of the circuit. So I'm going to demonstrate first that this indeed supplies 12 volts. So I have the potentiometer here set at a resistance, R2 resistance, to supply 12 volts to the load. So let's have a look. So I'm supplying 20 volts here in the VCC, and then I'm going to be measuring the voltage across the load, and hopefully you can see that there, it's 12.3 volts. So it's very close to the 12 volts that we want. Yep. Next, let's try and supply 15 volts and check that it doesn't change. So we've set the supply to 15 volts, and then across the load should also be 12 volts. Sorry. Yep, so 11.75, very close to 12. It doesn't change that much, which is what we expected. Next is if we change the load itself, it shouldn't change as well. So this one, the current connected resistor is a 1K, and I'm going to put a 2K in just to check that it's also supplying 12 volts and it doesn't change. So let's see. There should also be 12 volts across this. There you go. It's 11.8-ish. 11.8. And again, if we vary this to 20 volts, it'll be, again, 12.3. So very close to 12 volts. So this is a regulated power supply as we demonstrate that it works. Next, let's try to set another voltage through changing this potentiometer. So let me tweak the potentiometer. And I don't have a... so if we measure the... if we measure the resistance through it right now, you can see that it's about 3.2 kilo ohms, which is what we want here. And at 3 volts, it should be 987 ohms. So if we change this to 987 ohms, we should expect 3 volts across the load. So let's have a look and hope that we get that. So 987, 1K, 1K6, so we need more. Let's have a look. Okay, this is 0.8, and if we tweaked it a little bit to the other side, this may be too much. 1.3. Tweak it a little bit more. .16, another little bit of adjustment, and we're very close. All right, that's close enough. So this is currently 1K and 70 ohms, very close to 987. So if we turn this power on, we should expect approximately 3 volts across the resistor now. And let's try that. It's going to be slightly off because it's not exactly that resistor value, but there you go, 3.7 volts. 3.7 volts. And if we supplied 15 volts, we should also expect approximately 3.7 volts. There you go, 3.5 volts. 3.5. And once again, let's try to change the load. So from a 2K back to a 1K, and we should still see about 3.5 volts. There we go, 3.5 volts. Great. So yeah, that's a demonstration of the circuit working. Some things that I want to mention is that when I tried to check the filters working, I couldn't get it to work for some reason. So I had these two scopes connected across the load like this, and then I varied the input voltage a little bit to simulate noise, and it couldn't actually filter anything. I'm not sure why. Maybe it's because of the frequency, but when I also connected a series resistor, it still couldn't do the filter. So I don't know why the filter's not working. Maybe I'll figure this out in a future video. Thank you.